Okay, so let me do lecture 4. So here's another one more result I'll show in this class. So here I'll complete sort of the least squared estimation sort of facts about estimators. So here again, we'll do a simple result. Let's call it a proposition. We are calling all the results in orange. Let me put the orange one. Very good. So here what I'll say is that x beta is estimable and so you can always estimate x beta estimable, and its least squared estimate is given by, so I'll call this px y. So you have not seen this notation. We'll try and review it slowly over the course of the program, where px is the orthogonal projection. Orthogonal projection, sorry. Projection onto column space of X. Very good. So the nice theorem. So its result is quite nice. So you first know that x beta is estimable, and its least square estimate is given by this idea. So let's try and prove it. So we think a little bit. This should just follow from least squares theorem, right? Just follow that is the fact that least square estimate solves x transpose xy should immediately give it to you. So it actually does it. Let's just check it immediately. It's quite easy to do. So first thing you do is that you look at x beta. Wait, look at x beta. So what is that? So let's think of it as, let's say I'll write it down as a little bit more fancy fashion. Each row of x, I'll call it as P1 transpose. Okay, so P1 transpose, P2 transpose, all the way till last one is Pn transpose, right? Times beta. So when this is true, when x looks like this vector, that is P1 transpose all the way to Pn transpose. Okay. So x will look like this. But if you look carefully, this will actually force Pi transpose, that is, each of the Pi transpose is actually belongs to the column space of X transpose. Right? So if X transpose beta looks like this, then each of the elements of the rows belongs to the column space of X transpose. So 1 less than I less than equal to I. The standard fact, right? But that's if and only if we know if and only if x beta is estimable. That's exactly what it is, right? If x transpose y is equal to the appropriate column, that means x transpose. The straight form, nothing to be done. So estimable part is fairly easy. Now the least square estimate is where the orthogonal projection is, right? So now suppose, so simple exercise to think about, just think a little bit from. Now suppose beta hat is a solution to the normal equation. Okay. Then what happens now? That means r naught squared is equal to y minus x beta hat squared, right? This is the minimum attained by among all estimators y minus x beta, all parameters y minus x beta. Right? And you also know x beta hat is just a linear combination of the columns of X. So this belongs to the, and moreover, X beta hat belongs to the column space of X. And this also we know is the same as minimum over all possible beta in Rm of y minus x beta 2 squared. That's by the theorem or the way we design the theorem. But now, since x beta belongs to this guy, I can replace this guy also by everybody in the column space of X. So same as this implies R naught squared is equal to minimum over all vectors eta in the column space of X such that y minus eta 2 whole squared. Very good. Now, this is a linear algebra fact that if I take a vector, I can take its orthogonal projection and the other part is just 0 on the row space, right? So this is going to be equal to minimum of all. This is going to be equal to just the, if you want to find the, let's say you take a vector and you want to find the minimum among everybody in the column space of X, that's just going to be y minus the projection of X along the y of L2 squared. That's a linear algebra fact. Right? Where Px is the projection, orthogonal projection onto column space of X. It's the orthogonal projection of orthogonal projection onto column space of X. So that means that immediately you know that x beta hat has to be equal to pxy or px. This is px notation. So fairly elementary idea, moment you realize the fact. So all you use the fact is that if you have a, so the linear algebra fact that we use in the exercise is the following. That we used was the fact that if you have a plane that is like, that looks like a column space of X, this C of X, and if you have a vector Y that's sort of floating up like something like this, right? Then if you want to find the closest vector to Y on the column space of X, which is what you're trying to find here, right? So for that, what you have to do, you have to go plop this guy. You have to go plop this guy down with that, right? And that's the orthogonal projection. That's just px of y. That's what the result is, right? You know the result. That is, if you look at the geometry of it all, this is exactly what it is. Very cool. So that's the first linear algebra fact review that we did today. That is, if you take a vector outside the column space of X and you want to find the closest vector in column space of X that's to it, all you do is take the orthogonal projection of the vector onto the space, and that's what gives it to you. That's the pink vector. Very cool. Right. Let me just do a couple of more things about linear algebra, and I'll stop for the day, for the week. So here's something about, I just wanted to, since some of you have said you've seen, not seen this null space, column space, and so on and so forth, let's just sort of give a brief review of it. So let's take a 2 by 2 case. Let's say n equal to, let's say R2 case. So it's quite easy to zoom. And let's take a simple matrix. Let's say A2 cross 2, or let's call it X. In our case, we call it X, but let's call it A2 cross 2. A2 cross 2, let's take a simple matrix. Let's do, let's say 2 minus 1, let's say 4 minus 2. Let's take this matrix. So let me try to understand various things about this matrix. Right? So let me draw the axis in blue so that I have one axis kept separately. I need 4 colors. So let me call it row space. I'll do in blue. Then I'll do let's say column space of A in pink. Let me do the null space of A in orange, and let's see what happens. So let's draw the 2 axes here. And let's draw another vector here, axis here. So let's try and understand null space first, right? So what's null space of A? The null space of A is, let's call this as n of A. So let me call this as n of A. So n of A is what? So n of A is, so here's all the x here. So n of A is set of all x in R2 such that then A times x is 0. Right, that's what. So here, what's my matrix A? It is 2 minus 1, 4, 2. So let's go back to the matrix. So let's do this 2. So there's x in R2 such that 2 minus 1, 4, 2 times x1, x2 is equal to the 0 vector. Right? So let me just write the 0 vector in orange so that way everybody's going to go to 0. And I want to find all possible x that do the following job. That's my null space, right? So what does that give me? That's the same as saying that's if and only if you just do either a row echelon form or whatever you want to do, however you want to solve the system, it's same as saying 2x1 minus x2 is equal to 0. Right? That means x1 is a vector is a vector, let's say 1, and x2 is a 2 is a possible solution. Right? But in a sense, the null space is everybody on this vector 1, 2. Let's say 1 is here and 2 is somewhere here. So everybody on this vector is a solution to null space. So everybody on this line will be taken by the matrix A. If I hit anybody on this vector on the line A by the matrix A, they'll all land up at 0. That's a 0 vector. So all these people, A2x is going to go to 0. So everybody on this line will go to 0. The line is defined by the vector 1, 2. Very good. So that's clear. So that's the null space of A. So null space of A geometrically looks like this line. Now let's look at the column space of A. So what is the column space of A? Column space of A is the set of all B on that side, that is on this side, on the other side, on this side, right? On this side, the set of all B, let's say 2 cross 1, such that AX is equal to B. So that there is an X in R2 such that AX is equal to B. Now what does that mean? That means the same as saying set of all B2 cross 1 such that, why is it column space of A? Because there exists an X in R2 such that B is equal to X1 times the first column of A plus X2 times the second column of A. That's what it means, right? That's why it's called the column space of A. It's a linear combination of all the columns of A. Right? There's a fancy notation. AX equal to B is exactly B equal to X1 times. Right? So now I go here. What can I be? That means I have to be able to solve. That is, if I want to say the system is consistent, that means I have to solve for B. I take the matrix A, which is 2, 1, minus 1, 4 and minus 2. That's what I have here. 4 and 2, right? 4 and 2 or minus 2? 4 and minus 2, sorry, I made a mistake here. Sorry. That's same as saying, and I have a B1 and B2. Right? So I row reduce. Right. Then what do I get? I'll get 2 minus 1, B1 at the top. I do R2 goes to R2 minus 2 R1. And what do I get? I get B2 minus 2 B1, and I get 0, 0 here. Right? That means B is in the column space of A. If and only if B2 minus 2B1 is 0. That means B2 is equal to 2B1. So even example again is B1 is equal to 1 and B2 is equal to 2. So again, here also same thing happens. So everybody else is on this space. Right? This is the column, same line. The column. That means I take any other vector here that's going to get mapped onto this line. Right? That's what's happening. Right? So only these people are attainable by A in some sense. So it's kind of the range of A is 0 by everybody on this line, and anybody outside this line will get mapped somewhere here. Very cool. So that's column space of A. Very nice. Make it a little smaller so everything on one page. So we have here, we'll make it a little also smaller. Quite cool. So let's follow this way. Let's make this in pink so that we have an idea of what concept looks like. Very cool. And let's make the orange as the null space. It looks quite nice. So let's do what the row space of A is. Let's go to row space of A is what now? Row space of A is what? The row space of A is the span of the linear combinations of the rows of A, right? So the rows of A, I'll think of it again as column vectors. So it's the set of all vectors. Let's call it as, I'll write it as span of the vectors 2 minus 1 and 4 minus 2. 2 minus 1 and 4 minus 2. Right? That's going to be what now? That's going to be just linear combination 2 minus, but they're both the same. Is just going to be alpha times 2 minus 1, where alpha is the real number. That's what that's going to be. Just play a little bit of it. Right? That means what? You go here and you find out that this guy is just going to be this perpendicular vector right here. Right? Along this line. So that's the row space of A. So row space of A sits perpendicular to the null space of A. So from this, what all do you see now? What's the last space you can think about? If you want to think about last space, let's go another color. Let's say maybe what color can go? Maybe dark orange. Let's go. So here, last space you can think of it as the null space of A transpose. That's again the set of all X in 2 cross 1 again, such that, let me call this Y just to make sure it's on this side. Or let's say Y2 cross 1, such that A transpose Y is equal to 0. Okay. And that's a simple exercise you can think about. You can just do it. Simple as like, it's like beta times, it's just the same thing. It's just L transpose A is just a 1 comma minus 2. So it's just going to be orthogonal to this guy, right? So it's going to be on this side. This is going to be on top. null space of A transpose. So let's just do this. Let's do calculation. Let's just check it. So you have A transpose is 2 minus 1 and 4 minus 2 times y1, y2 is 0. That's if and only if minus y1 minus 2 y2 is 0. That means y1 is equal to minus 2 y2. So that's a line like this. So y1 is equal to 1, x1 is minus 2. This is what I have. So these are 4 fundamental subspaces, right, of matrix. Keep in mind. So if you haven't done a geometric picture like this, just make sure you do it once and then keep it in mind in the head. Okay. So now I list all the facts that I want to list. Okay. It's from the above picture. So above picture, what all do you understand? That you take the dimension of null space is 1, and there's a row space is a rank away. So nullity plus rank is 2. The same thing on both sides. So that's one theorem that we have. So now we just quote results from linear algebra. So keep it in mind. So null space of A, or the nullity of A, or the dimension of this. So nullity of A is equal to dimension of the null space of A, and the rank of A, which is the dimension of the row space of A. If you add these two guys, you get n. So that's the rank nullity theorem. So that you can see from this graph. Right? You can also show many things. You can also see that the row space of A is always orthogonal to the null space of A. Right? And you can see quite coolly from this graph that I've done here. Right? There's one more thing I wanted to show you. I'll just, because I use this fact that column space of X transpose X same as column space of X. So I'll give a short proof of that. So here's one simple fact. That let's say you take an X in the null space of A. Right? Then that implies that you have AX is equal to 0. Right? That means I can hit it with A transpose as well. So A transpose AX is also equal to 0. So that means X belongs to the null space of A transpose A. So if X is the null space of A, X is the null space of A transpose A. The reverse is immediately easy also. You take X in the null space of A, that means A transpose A transpose A, sorry. A transpose A, then A transpose A X is 0. And that's the same as saying X transpose A X is 0. That if you little bit, that's same as AX inner product with AX is 0. But if you take the same vector, that's the same as saying the L2 norm squared is 0. And that's the same as saying AX is 0. Cool. Right, very nice. That means X is in the null space of A. So from these two facts, what have we shown? The null space of A is the same as null space of A transpose A. Right? That's easy to see now. Right? The last part is fairly easy, that once you observe this, then you just think a little bit. So you observe that the column space of A is always contained in the column space of A transpose A. Right? That's one way it's clear, I think. Yeah. But the null spaces are the same, right? Therefore, rank nullity theorem will imply that column space of A transpose A will have to be equal to column space of A. Very cool.